Alright, hello everybody. Today we are back with another lesson on some mathematics and electrical engineering convention that we're going to need to know before we actually continue with the real content of this chapter. Alright, so first of all, we're going to talk about Euler's equation right here. So we're not really going to use Euler's equation that much directly in this unit, but it's very good to know, especially if you're an electrical engineer. But it is just a representation by which we can write cosine and sine together. Okay, and so as you can see, it is made out of a real part and an imaginary part. So it looks like a complex number essentially, but it can be written in polar form. Okay, and technically, I mean, this a right here is arbitrary. You know, it doesn't have to have the a, it's just multiplied across to show that it can be multiplied by some coefficient. Okay, and our theta can be expressed as omega, which is the angular frequency, which omega is also equal to 2 pi f, which is the regular frequency in hertz. Once again, we're not going to be explicitly looking into this, but it's very, very useful to know. And then we have our phase phi, and all of this is dependent on t time. Now, here is a very interesting portion. Now, if you've taken any kind of signal and systems class, some intro to electrical engineering class, or anything to really do with the convention of having complex exponentials, we have this right here. So the real part, right, is going to be the cosine part, which is this right here, and the imaginary part, which is denoted with this im, and these, squiggly brackets, curly braces, and we have the polar representation in here, and a sine theta. Now, this is actually technically wrong right here. The imaginary portion is this right here, okay? This j we know is root -1, but it's just a marker, okay, for our purposes, right? Because we want to think of this as a coordinate. So like this right here would be like, say, x, and this one would be y, okay? It's just saying that these two are distinct from one another, okay? And because for the longest time, I was confused about real and imaginary, because I was like, wait a second, like a to the j theta, the whole thing is a cosine theta plus j a sine theta, right? Why is it only equal to a cosine theta? Well, it's really the real part. And for you CS people, you can think of it like, I don't know, like a class, okay? And then so you have this class, and we're gonna name it complex, okay? And curly, and it's gonna have stuff in it, right? Real is equal to something, and imaginary is equal to something, right? And so you can actually get the real value, right? And you can get the imaginary part as well from the same thing. It's just that this m, right, is going to be denoted by this j. So this j guy doesn't really mean anything in this context, okay? At least that's how my professors, said it. Like, they didn't, that probably is mathematically incorrect, like saying that j doesn't mean anything, but for our purposes in this notation right here, we like to say that the imaginary part is just a sine theta. Okay, so that was a whole lot of yapping to hopefully get my point across, and hopefully that helps, because I had that wonderful confusion as well. So here's some common equations. So technically, if we didn't have this a right here, it would just be a 1, right? And the reason why we get these little equations, right, is if we take our Euler's equation and we just plug in that theta, let's say 0, plus ja sine theta, sine 0, then we're going to get just exactly that. This is just going to collapse to 1, this is just going to be 0. Okay, and then the same thing right here. If we have pi half, then the cosine portion is going to be 0, but the sine portion is going to be 1. So we're just going to be left with ja. Pi, you know, that cosine pi is going to be -1, and so we're going to get negative a. And 3 pi halves is going to be negative ja, because when you put 3 pi halves into sine, you're going to move that negative outside, and it's going to be minus ja. Now, here are a few identities that you would like to know as well, that cosine theta is equal to e to the j theta plus e to the minus j theta over 2, and sine theta e to the j theta minus e to the negative j theta over 2j. Now, once again, you're probably not going to be using this in this unit. I believe that I saw this used one time in a simplification of one of the circuits that we were doing, but I'm probably not going to make a problem like this, but it's, once again, it's very, very nice to know. And as such, I'm going to go ahead and derive this, because a lot of the times, or like I myself was like, where did these come from? They're so random. Well, they're not actually random, and it comes from e to the j theta. It comes from Euler's cosine theta plus j sine theta. So the first thing that you're going to want to ask yourself is, how can I get rid of this sine theta? Well, sine theta is an odd function, so because it's an odd function, we can say e to the minus j theta is equal to, and because cosine is an even function, we can stick that that negative theta in there, and it does nothing, okay? Plus, but in this case, when we stick the negative theta in here, I'm going to put the negative theta right there, when we stick in negative theta right here, it comes out, okay? This minus guy is going to make the sine theta negative. So it's going to be cosine theta minus j sine theta, okay? And then now we have our components to cancel out this j sine theta. All we have to do is say cosine theta is equal to e to the j theta minus e to the minus j theta. But here's the thing. The way that we did that was by adding these two guys together, right? Adding these guys together. This guy and this guy. And so this is actually 2 cosine theta. So we're going to have to say cosine theta is equal to e to the j theta minus e to the minus j theta over 2. And I'm glad that I'm recording this portion, because this is such an easy derivation, but I forget all the time, you know. And it's much better than memorizing this thing right here when you can actually derive it. So we're going to go ahead and derive sine. So what do we want to do? Well, we want to make sure that this cosine is negative now, and this sine theta will stay. Now, here's the thing. If we negate both of them, that's not going to change anything, because you just multiply both sides by negative. This will be negative right here, and you're not happy. But if we can instead negate this guy right here, well, they're opposite. So then that means that we can subtract one of these guys. So what we're going to do is we're going to say negative e to the negative j theta is equal to negative, and I'm going to open it in parentheses so that you can see it explicitly, minus j sine theta. Okay, and now we can say that the cosine theta term can be removed, whereas the sine theta term is just going to be added like last time. So negative e to negative j theta, and if we want to get this j sine theta, well, once again, we're going to have to add them up. Add these guys up. This e to j theta equals cosine theta plus j sine theta, and there you go. We get rid of our cosine that we did not want in this case, and we can add them up, and we get 2j sine theta is equal to e to the j theta minus e to the negative j theta. And if we want to move this 2j, we're just going to move it. Okay? So that's how you do, that's how you find these equations right here. Nice to keep in the back pocket of your mind, you know, but most likely not going to be useful in this course. Good to know. Okay, now this one we are going to use. I don't know the derivation for this one, so I'm just going to present it as is. But basically, it's going to be root a squared plus b squared, okay? And this is when we have a cosine and a sine added together, and the frequencies are the same, because you can turn time varying sinusoidal voltages and currents into phasor form only if the frequencies are the same. Okay, if they are not the same, then don't do the problem. I don't know how to do that. Anyway, so we have this theta right here, and theta is equal to tangent inverse minus b, negative b over a. Now, don't forget this negative b. Okay, so this negative changes the quadrant because we have, it's because of this sign right here. Because a cosine, a sine is equal to a cosine omega t minus 90 degrees. And if you actually, if you put in, yes, the 90 degrees is just, it's complementary of these guys, and so we're gonna have to add a negative for that. And finally, we have, actually probably should have showed this first, but you can take any sinusoid, like a cosine omega t plus theta, like just this regular old sinusoid, no multiplication, no addition, and you can write it like this to get the real part. Remember, we're getting the real part, and you can, and that will equal the complex phasor. Well, you can get the complex phasor from this, okay? So when you get this real part right here, so this right here is the complex phasor, or the complex amplitude, and this comes from, remember our Euler's, it was e to the j theta, right? That's actually kind of confusing. I should have made this phi. We had e to the j theta, right? And we said that theta is equal to omega t plus phi, right? Well, because of exponents, right, laws of exponents, we can make this a product of some complex, you know, this is not time varying anymore, okay? Because it's not time varying, it's just a constant, okay? And so we want this complex phasor right here, okay? And we're, for the time being, we're not going to consider this portion. We're just going to write this cosine omega t plus phi in its complex phasor form. So we are removing information for the time being, right? Because the idea is if everything in the circuit has the same frequency, then all we need to do is consider this complex phasor, okay? And that's just the extent that we're going to go into that. I'm sure that there are other YouTube videos that will explain a little more in depth if you have different frequencies, but for our purposes, for an ideal textbook, you know, problem, you're going to have the same frequencies, okay? So let's go ahead and simplify some of these guys right here. Now, remember, the form is just going to be a e to the j phi, okay? Where phi is this phase, and a is just the multiplied coefficient. So really, we're gonna call this like big phi, okay? And it's no longer in respects to time because we're bringing it into the frequency domain. We're saying that this is the frequency. All of it is going to be at the same frequency, and because all of it is going to be at the same frequency, we only care about the complex phasor, okay? We don't really care about this part. for now. I mean, in this special case. I want to make that clear. Okay, in this special case, we don't care about this guy, where all of the omegas are the same in the same circuit. And it's going to make a lot more sense in the next video. And so it's simply going to be 180 degrees. That's it. That's how you write the complex phasor for v of t of this case. Okay. All right. Now let's go ahead and do I of t. So we're just going to have a capital I for our phasor. I'm just going to call it that. And then it's 5 e to the j 92 degrees. Okay? Super simple. This is all we're doing. We're totally ignoring this portion of it. So this is only half of the story, okay? These are only half of the story. Now we're going to do the same thing over here. Oh, this is not in our correct form. All right, let's go ahead and simplify this guy. So we're going to use this identity right here. Okay, so we're going to take the square root of 6 squared plus 4 squared, and we're going to say cosine 10t plus, we'll say theta for now, and we're going to define theta over here as 10 tangent inverse minus 4 over 6, and that is going to equal negative 33.69 degrees. And let's check with our graph to make sure that we're in the right space. So this guy right here is changing where our quadrant is. So even though we had plus and plus right here, which would have put us in quadrant 1, we're actually going to be in quadrant 4. And does that make sense? Negative 33.69 degrees? Yes, that does make sense. So our theta right here is going to be minus 33.69 degrees. And this right here is going to be 36 plus 16 is root 52. And so our big V is going to be root 52 e to the negative j 33.69 degrees. Okay, now we have a sign right here. Now, in this case, I am always going to be converting a sine, a regular old sine, into a cosine. Okay, so to convert this into a cosine, we're going to use the idea that cosine theta is equal to sine theta minus 90 degrees, and that's it. So all we're going to do is add a negative 90 degrees into this argument. So it effectively becomes cosine 2 pi t plus 17 degrees minus 90 degrees. And simplifying this down, we're going to get negative 73 degrees. And so that's just going to equal to I 10 e to the negative j 73 degrees. Finally, we have this right here, and super simple. We literally just did a problem like this. We're just going to say minus 90 degrees here. And so I'm not even going to write out the cosine because all we care about is our phasor representation. 88 e to the negative j 90 degrees. And if you really wanted to, you could simplify this down further. You could say, I have a j 90 degrees, and I actually know what that looks like. A 90 degrees, j 90 degrees is just going to be ja, but there was a minus sign, so it's going to be minus ja. And so you could effectively write this same thing as v is equal to negative 88. Okay, if you really wanted to. And you could probably do the same thing with this 180 degrees. You said that, I know that e to the j pi is equal to -1, right? Right here, negative a. And so I can just go ahead and say this is equal to negative 8.34. So it's just very basic in this lesson. So next video, we are going to go ahead and actually solve some circuits with nodal analysis and loop analysis, the same old stuff. But we're also going to see that we can write our capacitors and inductors in a form that looks like that has these complex numbers, okay? And we're going to be converting between this and time so that we can solve these circuits in steady state much more simply, rather than depending on differential equations. Okay.